Welcome to our first video. Before we begin this journey into one of the most fascinating realms of science, I'd love to know where in the world you're watching from. Maybe you're in a quiet bedroom with the lights dimmed low, or perhaps you're on a late-night train ride with headphones blocking out the world, or curled up on a cozy couch with a warm drink nearby. Wherever you are, I hope you're comfortable, safe, and ready to gently drift into some deep thoughts about the nature of reality itself. If you enjoy these explorations into the mysteries of our universe, a like and subscribe really helps this channel continue bringing you more content like this. And to those of you already subscribed, thank you from the bottom of my heart. Your support means everything and allows us to keep exploring these incredible topics together. Now, fair warning, I'll try not to make tonight's topic so interesting that it keeps you wide awake, but if it does, at least you'll walk away with a better understanding of why the smallest particles in the universe refuse to follow the rules we thought were unbreakable. Why reality seems to hesitate and flicker until someone decides to look, and why the very act of observation appears to change what we're observing. A small price to pay for a potentially restless night, I'd say. Let's begin with something familiar, something comforting. The world we know, the one we can see with our eyes and touch with our hands, feels wonderfully solid and predictable. Drop a cup and it falls down, never up. Flip a coin and it will land on one side or the other, never both. Close your eyes and the moon doesn't vanish from the sky just because you're not looking at it anymore. These are the rules we've lived with since childhood, the certainties that make the world feel stable beneath our feet. For centuries, scientists built their understanding of the universe on these certainties. Isaac Newton gave us laws of motion that could predict exactly where a cannonball would land, or how the planets would move through space. Thermodynamics explained how heat flows and why engines work. James Clerk Maxwell unified electricity and magnetism into elegant equations that described light itself as an electromagnetic wave rippling through space. By the turn of the 20th century, physics felt almost complete, like a magnificent puzzle with only a few pieces left to place. Some scientists even believed that all the big questions had already been answered, and all that remained was to measure things more precisely and clean up a few odd details here and there. But those odd details, those small anomalies hiding in the corners of experiments, turned out to be cracks in the foundation of everything. When scientists began to look closer, much closer, peering into the behavior of atoms and light at scales smaller than anything visible to the human eye, they discovered something profoundly unsettling. The rules changed, the certainty vanished. Reality itself became something stranger, more fluid, more fundamentally weird than anyone had imagined. Light, which everyone knew was a wave, sometimes behaved like a particle. Particles, which were obviously tiny solid things, sometimes behaved like waves. Even more bizarrely, particles could exist in multiple places at once, at least until someone measured their position. And the act of measuring, of simply observing something, didn't just reveal information that was already there. It appeared to actually change the system, forcing it to choose one reality from many possibilities. This wasn't bad data. It wasn't faulty equipment. It was reproducible, measurable, undeniable. The universe, at its most fundamental level, operated according to rules so strange that they shattered centuries of carefully constructed physics. This discovery gave birth to quantum mechanics, a new way of understanding reality that replaced certainty with probability, precision with uncertainty, and classical cause and effect with something far more subtle and mysterious. In this video, we're going to drift gently through that quantum world together. There's no need to grasp every mathematical detail or memorize every scientist's name. We'll move slowly, softly, exploring one mystery at a time. From the earliest puzzles that knocked classical physics off its throne to the modern questions that still keep physicists awake at night, wondering and calculating and marveling at the sheer strangeness of it all. So settle in, get comfortable, maybe close your eyes if you'd like, and let's begin exploring a world where even empty space isn't truly empty, where particles dance between possibility and reality, and where everything you thought you knew about the universe turns out to be only probably true. The birth of quantum theory, Planck's revolution. At the dawn of the 20th century, physicists had every reason to feel confident. The laws of motion were well understood. Thermodynamics was tidy and complete. Light had been neatly tucked into Maxwell's framework of electromagnetic theory. It was a golden age of certainty, and some brilliant minds genuinely believed that all the fundamental questions of physics had been answered. What remained were just minor refinements, small measurements to be made more precise, a few loose ends to tie up like dust particles settling in an otherwise perfectly clean room. One of those supposedly minor loose ends involved a beautifully simple question: what happens when you heat something up? This seems almost trivially easy to answer. Heat a piece of metal or a lump of coal, and it glows. First a dull red, then brighter orange, then eventually a brilliant white, if you can get it hot enough. This glow is called blackbody radiation, and it comes from how hot objects emit electromagnetic radiation. It was easy to observe in laboratories, easy to reproduce, and it seemed like it should be straightforward to explain using the established laws of physics. Except it wasn't straightforward at all. The mathematics refused to cooperate in the most spectacular way possible. Classical physics, using all the well-tested equations that had worked brilliantly for so many other problems, predicted something absolutely absurd when applied to blackbody radiation. According to those formulas, as the temperature of a black body increases, it should emit more and more energy at shorter and shorter wavelengths. So far, so good. But the equations kept going. They predicted that at very high frequencies, particularly in the ultraviolet range of the electromagnetic spectrum, the energy output should become infinite. Not just very large, infinite. An impossible, ridiculous, reality-breaking infinity. This wasn't a small mathematical error you could fix with better measurements or slightly adjusted constants. This was a fundamental breakdown of the theory. The prediction led to infinite energy being radiated at high frequencies, a scenario so impossible and absurd that scientists gave it a memorable nickname: the ultraviolet catastrophe. It was catastrophic because no amount of tweaking the classical equations could fix it. The math simply spiraled into nonsense, while actual experiments showed that hot objects did not, in fact, radiate infinite energy. Reality and theory had completely parted ways. Enter Max Planck, a German theoretical physicist working in Berlin in the year 1899. Planck was not particularly radical or rebellious by nature. In fact, he was deeply committed to the classical worldview and had spent much of his career defending established physics. But Planck was also pragmatic and intellectually honest. When faced with the black body radiation problem, he decided to try something different, something that felt strange but might make the mathematics work. Planck introduced a small but revolutionary idea. What if energy couldn't be emitted in just any amount? What if, instead of flowing smoothly and continuously like water from a tap, energy came in tiny, discrete, indivisible packets, like coins that can't be split in half? These packets would represent the smallest possible units of energy. He called them quanta, from the Latin word for how much. This was a dramatic departure from everything classical physics assumed. Classical theory treated energy as continuous, able to take on any value along a smooth spectrum. But Planck's idea said no. Energy arrives in steps, in tiny jumps that depend on the frequency of the radiation. Each quantum of energy had a size determined by a new fundamental constant, a number so small it seemed almost insignificant, but would turn out to be one of the most important constants in all of physics. Today we call it Planck's constant, and its value is roughly 6.6 times 10 to the negative 34th joule seconds. It's unimaginably small, but it's absolutely fundamental. When Planck plugged his quantization idea into the equations for black body radiation, something remarkable happened. The infinity problem vanished. The ultraviolet catastrophe disappeared. The equations suddenly matched what experimenters were actually measuring in their laboratories. The curve of energy versus frequency came out exactly right. Planck had solved one of the most troubling problems in physics simply by suggesting that energy is quantized. But here's the fascinating part. Planck himself didn't quite believe his own solution. He viewed it as a mathematical trick, a clever way to make the numbers behave properly, but not necessarily a description of how the universe actually worked. He thought of quantization as a temporary fix, something that would eventually be replaced by a better, more classical explanation that wouldn't require such strange assumptions. In Planck's mind, this was just a placeholder, a patch over a crack that someone else would eventually repair properly. What Planck couldn't have known in 1900 was that his temporary fix would become the foundation stone of an entirely new branch of physics. His idea that energy comes in discrete packets laid the groundwork for quantum theory, a framework that would eventually unravel much of what classical physics had taken for granted. Sometimes the most revolutionary discoveries don't announce themselves with fanfare. Sometimes they slip quietly into a scientific paper, modest and unassuming, like a seed planted in soil that will one day grow into a forest. Looking back now, with over a century of hindsight, it's easy to see this as the moment when everything changed. But at the time it felt more like a strange footnote than a revolution. Planck hadn't set out to overturn the foundations of physics. He just wanted the mathematics to work, to stop producing absurd infinities, and start matching reality. But by introducing quantization, by suggesting that energy has a granular structure at its smallest scales, he had lit the first match in what would become a slow-burning fire, a fire that would eventually reshape our understanding of light, matter, space, and the very nature of reality itself. The idea sat there in the scientific literature, published in 1900, not making much noise, not shaking any foundations. There were no dramatic declarations, no immediate recognition of its importance. Just a small constant, a new way of thinking about energy, and a curious solution to a problem that had refused to go away. But from that moment forward, physics would never feel quite as finished as it once had. The age of certainty was over, though most people didn't realize it yet. The quantum revolution had begun, quietly, almost accidentally, in the careful work of a physicist who just wanted his equations to make sense: Einstein and the photoelectric effect. By the early 1900s, the scientific world thought it had pretty much figured out. Thanks to Maxwell's brilliant equations, physicists knew that light behaved as a wave, an elegant ripple in the electromagnetic field that traveled through space at a fixed speed. Light bent around corners, bounced off surfaces, diffracted through narrow slits, and interfered with itself in beautiful patterns, just like any proper wave should. After Max Planck's introduction of energy quanta, most scientists assumed things would settle down into a new, slightly adjusted version of normal. A few equations would be refined. The quantization idea would be properly understood in classical terms, and physics would continue marching forward along familiar paths. But then came a strange phenomenon involving light, metal, and electrons that refused to make sense. It was called the photoelectric effect, and it worked like this: shine light on a metal surface, and electrons can be ejected from that metal. This seemed reasonable enough. Light carries energy, and when that energy hits electrons in the metal, it should be able to knock them loose. No mystery there, at least not at first glance. According to wave theory, which everyone believed explained light perfectly, increasing the brightness or intensity of the light should increase the energy transferred to the electrons. A brighter wave should shake electrons loose more effectively, giving them more energy as they flew away from the metal surface. It was like hitting a bell with a stronger hammer. More energy in should equal more energy out. Simple, predictable, classical. But experiments told a completely different story. When researchers actually measured what happened, they found something deeply puzzling. Shining brighter light on the metal didn't necessarily eject electrons with more energy. In fact, there seemed to be a sharp threshold based not on brightness but on the frequency of the light. If the light's frequency was below a certain value, even an incredibly bright beam would do nothing at all. 0 electrons ejected, regardless of intensity. But if the light's frequency was above that threshold, even a dim beam could knock electrons free with considerable energy. This made absolutely no sense in wave theory. Brightness should matter. Intensity should matter. But instead, frequency was the key, and the threshold was sharp and unforgiving. Low-frequency light was powerless no matter how bright. High-frequency light worked even when dim. Classical wave theory had no explanation for this behavior. The phenomenon had become a full-blown mystery, and physicists had no idea why their trusted equations were failing. Enter Albert Einstein, whose name would become synonymous with genius and revolutionary thinking. In 1905, often called his miracle year because he published multiple groundbreaking papers in a single year, Einstein tackled the photoelectric effect with a bold and counterintuitive idea. What if light wasn't just a wave? What if, under certain circumstances, it behaved like a particle? Not a wave carrying energy smoothly and continuously, but rather a collection of tiny packets of energy traveling in straight lines like bullets. Einstein proposed that light was made up of individual quanta of energy, which he called light quanta. Today we call them photons. Each photon carried a specific amount of energy determined by its frequency, following Planck's relationship that energy equals Planck's constant times frequency. If a photon had enough energy, it could knock an electron loose from a metal surface in a single collision. If the photon didn't have enough energy, No amount of photons, no matter how many hit the metal, could do the job. Think of it like trying to open a locked door with a pile of keys. If none of the keys fit the lock, it doesn't matter if you have one key or a million keys. You're not getting through that door. But if you have the right key, just one of them, the door opens. Similarly, if individual photons don't carry enough energy to overcome the binding force holding electrons in the metal, cranking up the brightness just means more low-energy photons hitting the surface, and more isn't better when you don't have enough energy per photon. But give each photon enough energy by increasing the frequency, and now even a few photons can do the job. Einstein's photon explanation elegantly solved the photoelectric effect mystery. The energy of each photon depended on frequency, exactly as the experiment showed. Low-frequency photons simply didn't pack enough punch, explaining why low-frequency light was ineffective regardless of brightness. High-frequency photons carried enough energy to liberate electrons, explaining why even dim high-frequency light worked. The threshold behavior fell naturally out of Einstein's particle model of light, but this idea was controversial, almost heretical at the time. Many physicists clung tightly to the wave model of light. After all, light clearly did exhibit wave-like behavior in numerous experiments. Diffraction, interference, all the classic wave phenomena were undeniable. If light was really made of particles, how could it also act like a wave? Waves and particles were fundamentally different things in classical physics. A wave spreads out, a particle is localized. Waves interfere, particles collide. You couldn't be both. Einstein wasn't denying the wave nature of light. Instead, he was proposing something far stranger and more radical. Light, he said, was both a wave and a particle, depending on how you looked at it and what experiment you performed. This wasn't just a matter of imprecise language or metaphor. Einstein was suggesting that wave-particle duality was fundamental to the nature of light itself. Under some conditions and in some experiments, light behaves like a wave. Under other conditions and in other experiments, it behaves like a particle, not sometimes one or the other by chance, but genuinely exhibiting both properties as intrinsic aspects of its nature. Imagine a beam of sunlight streaming through a window. At a macroscopic level, it spreads and ripples like a wave, bouncing off dust particles, bending around corners, creating interference patterns. But zoom in to the quantum level, way down where individual interactions happen, and you'd find discrete quanta of energy, individual photons with specific frequencies, colliding with atoms and changing the world one interaction at a time. Both descriptions are true. Both are aspects of what light is. This concept of wave-particle duality challenged the very categories humans use to describe reality. In the classical world, things are either particles or waves. They're either matter or energy. They're either localized or spread out. But the quantum world doesn't ask for permission to fit into our neat boxes. It simply is what it is. And what it is turns out to be weirder and more nuanced than classical intuition ever imagined. The impact of Einstein's photon explanation was massive. His work on the photoelectric effect didn't just solve one experimental puzzle. It helped establish the reality of quantization, the idea that energy comes in discrete chunks at the smallest scales. It opened the door to understanding light and matter in fundamentally new ways. And in 1921, Albert Einstein received the Nobel Prize in Physics. Many people assume he won it for his theory of relativity, which revolutionized our understanding of space, time, and gravity. But no, the Nobel Committee awarded the prize for his explanation of the photoelectric effect. That's how significant this discovery was. It fundamentally changed how we understand light, energy, and the quantum nature of reality. Still, even Einstein found the quantum world uncomfortable as it developed beyond his initial contributions. He became increasingly uneasy with the probabilistic interpretations that would follow in later years, famously declaring that God does not play dice with the universe. He wanted determinism, predictability, a universe that made sense in classical terms. But dice or not, the rules were changing beneath everyone's feet. Light, the phenomenon that illuminates our world and makes vision possible, refused to fit into any tidy conceptual box. It came in quanta, discrete packets of energy. It danced and interfered as a wave. It collided like a particle. It shimmered between states and descriptions, revealing just enough to keep scientists endlessly curious, and just enough to keep everyone fundamentally unsure about what light actually was at its core. What began as a simple experiment with light hitting metal ended up shaking the foundations of physics. Because if light could behave this way, exhibiting both continuous and discrete properties, both spread-out wave nature and point-like particle nature, then what else might be lurking in the universe, waiting to break all the comfortable rules we thought were unbreakable? The double-slit experiment, reality's greatest mystery. Imagine you're setting up an experiment on a table. You place a light source at one end, cut two narrow slits into a piece of cardboard, and position a screen behind those slits to catch whatever comes through. Not exactly thrilling, is it? It's just two holes in cardboard and a light. You could do this in your garage with simple equipment, and yet, in this humble, almost embarrassingly simple arrangement, we find one of the most mind-bending, reality-challenging experiments in all of science. The double-slit experiment has become legendary in physics, not because it's complicated, but because what it reveals is so profoundly strange that it forces us to question everything we think we know about how reality works. Some physicists have called it the most dramatic experiment in all of science. It's been repeated countless times, refined and improved with increasingly sophisticated equipment, and the results remain just as bizarre and unsettling as they were when scientists first started grappling with them over a century ago. Let's start with what we'd expect if physics worked the way our intuition suggests. In the classical world, waves and particles behave very differently. Take a wave, like the ripples on a pond or sound traveling through air. Waves spread out. They overlap with each other. When two waves meet, they can interfere, reinforcing where their peaks align and cancelling out where a peak meets a trough. Imagine ocean waves passing through two openings in a barrier. The waves emerge on the other side, spread out, and create a complex pattern of peaks and troughs. Regions of constructive interference where the water is choppy, and regions of destructive interference where the water is calmer. This is classic wave behavior, well understood, nothing surprising. Now imagine particles, tiny solid things like miniature rubber balls. Fire them at a wall with two openings. Some balls go through the left slit, some go through the right slit, and they land on a screen behind the slits in two distinct clusters, one cluster roughly behind each opening. Particles don't overlap or interfere with each other. They travel in straight lines, collide with things, and land in specific spots. Straightforward, predictable, no surprises. So what happens when you perform this experiment with light? When scientists first shone light through two narrow slits, they expected it to behave like a wave since Maxwell's equations had established light as an electromagnetic wave. And it did. The light passing through the slits spread out and created an interference pattern on the screen behind them, alternating bright and dark bands where the light waves overlapped constructively and destructively. Bright bands where peaks met peaks, dark bands where peaks met troughs and cancelled out. Textbook wave behavior. Everything made sense. But then things got weird, and I mean really weird. Using increasingly sensitive equipment, researchers gradually turned down the intensity of the light source until it was firing just one photon at a time. Instead of a continuous stream of light, individual particles of light were making their way toward the slits one by one, with measurable gaps between them. Now, you'd expect these lone photons to act like classical particles. Each photon should go through one slit or the other, left or right, and over time you should see two bright spots on the screen, one behind each slit, exactly like those rubber balls. But that's not what happened. Not even close. Even when sent through one photon at a time, even when there was no other photon anywhere near the apparatus to interact with, the photons gradually built up the exact same interference pattern as before. The alternating bright and dark bands emerged just as if continuous waves were passing through. But there were no continuous waves. These were individual particles arriving one at a time. How could a single photon create an interference pattern? What was it interfering with? The only possible explanation seemed to be that each photon was somehow going through both slits simultaneously. Like a ghost of itself, it explored multiple paths at once. And when those paths recombined on the other side, they interfered with each other. A single photon, acting like a wave, spread across both slits, interfering with itself before landing at a single point on the screen. It's as if the photon took every possible path through the apparatus and all those possibilities combined to determine where it would finally appear. If that wasn't strange enough, physicists decided to peek behind the curtain. They placed detectors right at the slits to observe which path each photon actually took. Surely, they thought, we can just measure this directly and settle the question once and for all. Did the photon go through the left slit, the right slit, or somehow both? But when they turned on the detectors to watch, the interference pattern vanished completely. As soon as the photons were observed, as soon as the detectors determined which slit each photon passed through, the photons stopped behaving like waves. They acted like ordinary particles again, each going through one slit or the other and landing in one of two clumps behind those slits. No more interference. No more mysterious wave behavior. Reality had been caught in the act, and it immediately straightened up and acted normal. Turn off the detectors, stop observing the paths, and the interference pattern returned. Turn the detectors back on, resume observation, and the pattern vanished again. It was repeatable, consistent, utterly bizarre. The very act of measuring which path the photon took seemed to change how the photon behaved. Not because the measurement physically disturbed the photon in some crude mechanical way. These were carefully designed experiments with minimally invasive detection methods. The issue wasn't how we observed, but that we observed at all. It seemed that the mere knowledge of the photon's path, the potential to know where it went, was enough to collapse its wave-like behavior into a particle-like state. The universe appeared to care whether it was being watched, whether information about the quantum system state was being extracted and recorded. When unobserved, the photon existed in a superposition of states, genuinely taking both paths simultaneously according to quantum mechanics. When observed, it had to choose one path, and the wave function collapsed into a single definite outcome. This wasn't a fluke or experimental error or a problem with one particular setup. The double-slit experiment has been repeated thousands of times with photons, electrons, neutrons, and even entire molecules made up of dozens of atoms. Every single time, the result is the same. When left unobserved, quantum particles act like waves and create interference patterns. When observed, they act like classical particles and fall into distinct groups. The effect is consistent, reproducible, and fundamentally unsettling. The double-slit experiment sits at the very heart of quantum mechanics and resists every attempt to explain it away with familiar classical concepts. It suggests that, at the smallest scales, particles don't follow strict predetermined paths from point A to point B. Instead, they exist as a spread of possibilities, a shimmering cloud of potential outcomes. Every possible path is somehow part of the particle's reality until a measurement forces that cloud to collapse into a single definite answer. Some physicists have tried to picture this by imagining the particle as a wave that splits at the slits and then reunites on the far side. Others prefer the language of probability, describing the wave function as a mathematical tool for predicting outcomes without necessarily representing physical waves in space. Still others, particularly those in the many worlds interpretation camp, imagine that each possible path corresponds to a different branch of reality, and what we call measurement is simply finding ourselves in one particular branch. But whatever interpretation you prefer, whatever philosophical stance you take on the nature of quantum mechanics, the experimental facts remain unchanged. Until we observe it, the particle doesn't commit to any single state or location or path. It exists in superposition, genuinely occupying multiple states simultaneously. Only when measurement occurs does reality crystallize into something definite. What began as a simple test of whether light behaved like a wave or a particle has turned into a profound mystery about the nature of reality itself. Is observation an active part of shaping the physical world? Does information have power over existence? Is reality fundamentally uncertain, probabilistic, undetermined until we force it to reveal itself through measurement? These aren't just philosophical questions debated in academic circles. They're scientific questions rooted in experiment, measured and confirmed in laboratories around the world. The double-slit experiment doesn't give us clear, comfortable answers, but it does give us one powerful and unsettling insight. The universe at its core is not a clockwork machine with gears turning along predetermined paths. It's a strange and shimmering field of possibilities woven from probabilities and superpositions. And somehow, mysteriously, it responds in curious ways to our gaze, to our measurements, to our attempts to pin it down and know what's really happening. With just two slits, a light source and a screen, we've discovered that the universe winks at us when we're not looking and snaps to attention when we are. Reality, it turns out, is far stranger than anyone imagined. Heisenberg's uncertainty principle. In the everyday world of coffee cups and bicycles and cars, you can know where something is and how fast it's going at the same time. In fact, this seems so obvious it barely needs stating. A radar gun measures a car's speed while GPS tells you exactly where that car is located. No contradiction, no mystery. If you know all the properties of an object with perfect precision, you can predict exactly where it will be in the future and exactly how it will behave. This is the clockwork universe of classical mechanics, deterministic and predictable down to the smallest detail. But the quantum world doesn't play by those rules. In the 1920s, Werner Heisenberg introduced a principle so strange, so fundamentally challenging to our intuitions, that it still gives students and scientists alike moments of deep pause and reflection. It's called the Heisenberg uncertainty principle, and it tells us that at the most fundamental level of reality, there are hard limits to what we can know. Not limits imposed by clumsy measuring devices or insufficient technology, but limits woven into the very fabric of the universe itself. Specifically, Heisenberg's principle states this: the more precisely we know a particle's position, the less precisely we can know its momentum, which is its mass times its velocity, and vice versa. It's a trade-off, a cosmic give and take. Pin down where a particle is with great accuracy, and its momentum becomes increasingly uncertain. Measure its momentum precisely, and its position becomes fuzzy and ill-defined. There's a minimum product of these uncertainties, and that minimum is set by Planck's constant divided by 4 times pi, a tiny number that nevertheless represents an unbreakable barrier to knowledge. Now, in our everyday experience, this sounds almost nonsensical. How could knowing where something is make you unsure about how fast it's moving? If you watch a train pull into a station, you can see both its location and estimate its speed. You can measure both with instruments. There's no cosmic prohibition against knowing both, but at the quantum scale, at the level of electrons and photons and atoms, this limitation is real, unavoidable, and profound. Here's the key insight. This uncertainty isn't about our measuring tools being inadequate. It's not a practical limitation that better technology could overcome. The uncertainty is intrinsic to quantum systems. It's part of how they exist, even with perfect measuring instruments that don't disturb the system at all. Even with ideal non-invasive observation methods, the uncertainty would still be there, baked into the quantum nature of particles themselves. Let's try to understand why. Say you want to observe an electron, to figure out where it is and how fast it's moving. To see it, you need to shine light on it, to bounce photons off it so they reach your detector and form an image. But photons carry energy and momentum. When a photon collides with an electron, it transfers some of that momentum to the electron, changing how the electron is moving. It's a bit like trying to locate a soap bubble in a dark room by throwing tennis balls at it. Sure, you'll find the bubble when a tennis ball hits it, but you'll also destroy or dramatically change the bubble in the process. The act of measurement unavoidably disturbs what you're trying to measure. But Heisenberg's insight went deeper than just measurement disturbance. His principle isn't merely about the practical difficulty of observation. It's built into the mathematical structure of quantum mechanics. Even if you could somehow observe without disturbing, even through some magical non-invasive method, the uncertainty would persist. The reason lies in the wave nature of quantum particles. Quantum mechanics describes particles using wave functions, mathematical expressions that contain all the information we can have about a system. These wave functions are spread out in space. They're not sharp points but extended distributions of probability. Now, imagine trying to localize a wave to figure out exactly where it is. If you want to pinpoint a specific location, you need to construct a wave packet that's very narrow, concentrated in a small region of space. But to build such a narrow wave packet mathematically, you need to combine waves of many different wavelengths, many different frequencies and momenta. The wave gets choppy, and that choppiness means a large uncertainty in momentum. Conversely, if you want to know the momentum precisely, you want a nice smooth wave with a single well-defined wavelength. But a smooth wave extends over a large region of space, which means you can't say precisely where the particle is. It's spread out. The mathematical structure of waves imposes this trade-off. Position and momentum are described by wave functions that are related by something called a Fourier transform in mathematics, and that relationship guarantees that making one sharply defined makes the other fuzzy. It's not a bug in nature, it's a feature, a fundamental property of wave-based descriptions. The uncertainty principle can be written mathematically as the product of the uncertainty in position and the uncertainty in momentum being greater than or equal to Planck's constant divided by 4 pi. Planck's constant is incredibly small, around 6.6 times 10 to the negative 34 joule-seconds. In our everyday macroscopic world, this number is so tiny that the uncertainty is negligible. You can measure the position and speed of a baseball or a car or a planet to extraordinary precision without ever bumping into quantum limits. The effects are simply too small to notice at human scales. But at the scale of electrons, atoms, and subatomic particles, where masses and distances are vanishingly small, the uncertainty becomes impossible to ignore. It shapes behavior at the quantum level. If you try to trap a particle in a very small space, confining it tightly to nail down its position, it starts to behave wildly. Its momentum becomes highly uncertain, which means it zips around unpredictably with a range of possible velocities. Try to pin it down further, make the box even smaller, and the particle resists even more. It's as though nature fundamentally dislikes being told exactly where things are and exactly how they're moving. There's an inherent fuzziness, a blurriness that can't be wiped away. This has profound consequences. Consider why atoms don't collapse. You might wonder, if electrons are negatively charged and the nucleus is positively charged and opposite charges attract, why don't electrons just spiral into the nucleus and stay there? Classical physics has no good answer, but quantum mechanics, with the uncertainty principle, explains it beautifully. If an electron were to fall into the nucleus and remain there, its position would be known with extremely high precision, confined to the tiny volume of the nucleus. That would require its momentum uncertainty to become enormous, which corresponds to an enormous amount of kinetic energy, far more energy than the electron actually has. Nature says no. The uncertainty principle creates a kind of quantum pressure, a resistance to being overly confined. Electrons settle into specific orbitals around the nucleus, regions where they can exist in stable probability clouds without violating the uncertainty constraints. Atoms are stable because of quantum uncertainty. The uncertainty principle also applies to other pairs of properties, energy and time, for instance. The more precisely you know the energy of a quantum state, the less precisely you can know when that state exists or how long it lasts. This has implications for everything from spectral line widths in atomic physics to the fleeting existence of virtual particles in quantum field theory. In each case, uncertainty in one property means unavoidable uncertainty in its conjugate partner. There's something almost philosophically comforting about the uncertainty principle. Even though it denies us perfect knowledge, it tells us that the universe isn't mechanistic in the way Newton imagined, where perfect knowledge of the present allows perfect prediction of the future. Quantum mechanics introduces an intrinsic unpredictability, a fundamental limit to how much we can know and control. But that unpredictability isn't chaos. It's structured. It follows precise mathematical rules. The uncertainty is constrained, governed by relationships that can be calculated and tested. In a strange way, the uncertainty principle invites us to make peace with not knowing everything. It asks us to accept that some aspects of nature will always remain just slightly out of reach, shimmering in a haze of possibility and probability. Reality at the quantum level has texture, softness, a graceful fuzziness, and perhaps surprisingly, this fuzziness is essential. Without it, atoms wouldn't be stable. Chemistry wouldn't work. Quantum tunneling, which allows particles to pass through barriers they classically shouldn't be able to cross, wouldn't happen. Life itself, which depends on chemical reactions that occur at the quantum level, might not be possible. The uncertainty principle is a reminder that some of the deepest truths are not sharp-edged, but cloudy, rippling, and unresolved. And maybe that's exactly why they're so beautiful. Werner Heisenberg showed us that the universe has built-in limits, boundaries to knowledge that we can never cross, no matter how clever we become or how powerful our instruments get. But within those limits, within that uncertainty, lies all the richness and complexity that makes reality interesting, surprising, and endlessly worth exploring. Quantum superposition. Being in multiple places. In our everyday experience, things tend to be in one definite state or another. A coin lands heads or tails, not both. A light switch is on or off. Your tea is hot or cold, though admittedly sometimes it's lukewarm, which is technically a temperature in between. But generally speaking, objects have definite properties. They're here or there. They're this way or that way. Classical physics reflects this intuition. Particles have positions. Objects have states. Everything is determined and definite, even if we don't always know what that definite state is. But in the quantum world, this tidy division of reality into distinct states breaks down completely. Objects at the smallest scales don't always pick a side. They can hover in a strange in-between, a blend of multiple possibilities existing simultaneously. This is quantum superposition, one of the most counterintuitive and fascinating concepts in all of physics. To picture superposition, imagine flipping a coin in the classical world. Once the coin leaves your hand, it follows a specific trajectory through the air. It spins, tumbles, and eventually lands on one side or the other. You might not know whether it's heads or tails until it lands and you look at it, but the coin was always going to land on whatever side it landed on. The outcome was determined by initial conditions, how you flipped it, air resistance, gravity, all the physical forces. Your ignorance about the result doesn't mean the coin was ever in two states at once. It just means you didn't have enough information to predict the outcome. Quantum systems work completely differently. If you could flip a quantum coin, not a real coin but a quantum system that has two possible outcomes, it wouldn't secretly be heads or tails while spinning through the air. Instead, until you observe it, until you measure which state it's in, it would genuinely exist in a superposition of both heads and tails simultaneously, not undecided, not flipping rapidly back and forth, actually, physically, in both states at once according to the mathematics of quantum mechanics. It's not that we don't know which it is. It genuinely is both, at least until measurement forces it to pick one. When you finally look at the quantum coin, When you perform a measurement to see what state it's in, the superposition collapses. The quantum system suddenly commits to one outcome, and that becomes the reality you observe. Before measurement, it was a probabilistic blend of possibilities. After measurement, it's a single definite answer. This collapse is instantaneous and absolute, and it's one of the deep mysteries of quantum mechanics that physicists still debate. Superposition was first recognized and formalized in the early development of quantum theory, particularly in the 1920s and 30s, as physicists worked out the mathematics of wave functions and quantum states. Particles like electrons and photons are described by these wave functions, which are mathematical objects encoding probabilities. Each possible state, each possible outcome, each possible property is part of the wave function. All those possibilities coexist in superposition until measurement selects one of them. You might visualize it like a foggy landscape with many possible hilltops. Before measurement, the particle isn't walking along a single path to one particular hilltop. It's more like it's spread out, smeared across every possible route, present on every hilltop simultaneously. When you interact with it, when you measure its position or momentum or spin, that fog suddenly snaps into focus, like lightning illuminating just one hilltop in the mist. That's where you find the particle. All the other possibilities vanish. This concept led to one of the most famous thought experiments in physics, devised by Erwin Schrödinger to illustrate what he saw as the absurdity of applying quantum rules to everyday objects. Suppose you place a cat in a sealed box along with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector notices, triggers a mechanism that breaks the vial, and the cat dies. If the atom doesn't decay, the cat lives. Quantum mechanics says that until the atom is observed, it exists in a superposition of decayed and not decayed states. If you take the logic seriously, the entire system, including the cat, should also be in a superposition. The cat would be both alive and dead simultaneously until someone opens the box and makes an observation. Schrödinger didn't propose this as a real experiment. He was highlighting what he felt was an absurdity, the strangeness of extending quantum rules to macroscopic objects. But the thought experiment stuck because it vividly captures the weirdness of superposition. It's become a cultural touchstone, mentioned in countless books, films, and conversations as shorthand for quantum strangeness. Of course, real cats don't exist in superposition of life and death. Macroscopic objects interact constantly with their environment, which effectively measures them and causes decoherence, collapsing any quantum superposition almost instantly. The quantum fog only persists when systems are isolated from environmental interactions. But for quantum particles, for electrons and photons and atoms, superposition is not just an abstract mathematical curiosity. It's a powerful, exploitable feature that underlies modern quantum technology. Take quantum computing, for example. In a classical computer, the smallest unit of information is a bit, which can be either 0 or 1. Everything your phone or laptop does is built on combinations of billions of these binary bits, flipping between two states to perform calculations and store data. Quantum computers use qubits instead, quantum bits, and a qubit, thanks to superposition, can exist as 0 and 1 simultaneously. It's not switching between them. It's not half and half in some vague sense. It's in a genuine quantum superposition where both states coexist. This means a single qubit holds more information than a classical bit in a certain sense. When you have multiple qubits and they become entangled with each other, they can represent a vast number of states at once. 2 qubits can represent 4 states simultaneously. 3 qubits can represent 8 states. 10 qubits can represent over 1,000 states. The number grows exponentially, giving quantum computers the potential to perform certain types of calculations far more efficiently than classical computers. It's not magic. It's just mathematics that plays by quantum rules. Problems involving complex systems, like simulating molecular behavior or optimizing large networks or searching through massive datasets, suddenly become tractable when you can use superposition to explore many possibilities in parallel. Quantum algorithms like Shor's algorithm for factoring large numbers and Grover's algorithm for searching unsorted databases leverage superposition to achieve speedups that would be impossible classically. Superposition also plays a crucial role in quantum cryptography, where it helps create secure communication channels. If someone tries to intercept quantum information, they have to measure it, which collapses the superposition and disturbs the system in a detectable way. This makes quantum key distribution provably secure in ways classical encryption can never match. Similarly, quantum sensing uses superposition to detect incredibly small changes in magnetical gravitational fields with unprecedented sensitivity. These aren't science fiction concepts. They're real technologies being developed and deployed right now, all hinging on our ability to prepare, maintain, and measure quantum superpositions. But superposition is delicate, almost heartbreakingly fragile. Quantum systems are easily disturbed. The slightest interaction with the environment, stray photons bouncing off the system, vibrations, thermal fluctuations, even air molecules passing nearby, can collapse the wave function and destroy the superposition. This process is called decoherence, and it's one of the biggest challenges in building stable quantum systems. Maintaining coherent superpositions long enough to perform useful calculations requires extraordinary care. Ultra-cold temperatures, vacuum chambers, electromagnetic shielding, error correction schemes. It's like trying to balance a feather on the tip of a needle while someone sneezes in the next room. The superposition vanishes at the slightest provocation. That fragility is part of what makes quantum systems so fascinating and so difficult to work with. They offer incredible power and capabilities, but only under very precise and carefully controlled conditions. They give us access to probabilities and parallelism, but they demand isolation and precision. They force us to rethink what it means to say that something is, to question our assumptions about definite states and classical reality. Superposition also leads to deep philosophical questions. If particles can exist in multiple states, is that really reality? Or is it just a reflection of our ignorance, our lack of knowledge about what's actually happening? Different interpretations of quantum mechanics give different answers. Some say the wave function represents our knowledge, our best guess about a system until we measure it. Others argue the wave function is physically real, and particles genuinely are in multiple states until forced to choose. Yet others propose that every possible outcome actually occurs in separate branching realities. And superposition simply reflects the fact that all branches coexist. Whatever the correct interpretation, superposition invites us to loosen our grip on classical logic and embrace a more fluid understanding of reality. It tells us that opposites can coexist, that systems can be this and that, here and there, yes and no, all at the same time. Reality at its core isn't a single thread, but a rich multiplicity of possibilities overlapping and unresolved, until observation pulls one thread loose from the bundle. It's strange, deeply uncomfortable at first, but also beautiful in its own way. Because in this strange principle of superposition, we find a universe that isn't rigid and mechanical, but flexible and probabilistic. A universe that allows for contradiction and uncertainty, not as flaws, but as essential features. And in doing so, it opens up entirely new ways to compute, communicate, measure, and explore what's possible when reality refuses to commit to just one answer until we force it to choose. Quantum entanglement. Spooky action at a distance. Imagine you have two gloves, one left-handed and one right-handed. You put each glove into a separate box without looking. Shuffle the boxes around so you don't know which glove is in which box, and then send one box to someone on the other side of the planet. Later, you open your box and discover it contains the left-handed glove. Instantly, you know with absolute certainty that the other box must contain the right-handed glove. This seems perfectly reasonable, even trivial. The gloves were always one left and one right. Opening your box didn't change anything about the other glove. It just revealed information you already had in principle. No mystery, no magic, just logic. But quantum entanglement isn't like that at all. Entangled particles aren't like pre-sorted gloves sitting in boxes waiting to be revealed. They're more like gloves that don't decide which hand they are until you open one of the boxes. And somehow, impossibly, the instant you open one box and find a left-handed glove, the other glove becomes right-handed, no matter how far away it is. The measurement of one particle doesn't just reveal information. It actually determines the state of the other particle instantaneously, even if they're separated by distances so vast that light itself couldn't travel between them in any relevant time frame. This is quantum entanglement, and it is genuinely one of the strangest, most baffling, most reality-defying features of the quantum world. Even Albert Einstein, who helped lay the foundations of quantum theory with his work on the photoelectric effect, found entanglement deeply troubling and refused to accept it as a complete description of reality. Here's how entanglement works. When two quantum particles interact in certain ways, perhaps by being created together in a single event or by colliding under specific conditions, they can become entangled. This means their quantum states become linked, correlated in ways that defy classical explanation. The particles no longer have independent properties. Instead, they form a single quantum system described by a joint wave function, even if they're subsequently separated by enormous distances. Consider two entangled photons with correlated polarizations. Quantum mechanics tells us that before measurement, neither photon has a definite polarization. They exist in a superposition of all possible polarization states, but they're entangled, meaning their states are linked. If you measure one photon and find it's polarized vertically, the other photon will instantly be found to be polarized horizontally, not because it was always horizontally polarized and you just didn't know. According to quantum theory, it genuinely had no definite polarization until the first photon was measured. The act of measuring one particle instantaneously affects the other. The particles might be in Paris and Tokyo, millions of miles apart. There's no signal traveling between them, no hidden communication, no time for information to pass from one to the other. And yet, the moment you measure the first photon, the second photon's state becomes determined. It's as if the universe updates both particles simultaneously. with no delay, no respect for the speed of light limit that governs all other physical processes. Einstein famously called this spooky action at a distance, and he hated it. He believed deeply in locality. The principle that physical processes at one location can't instantly affect things at distant locations. Locality is a cornerstone of relativity. Nothing, not even information, can travel faster than light. Objects are only directly influenced by their immediate surroundings. The idea that two particles could coordinate their states instantaneously across arbitrary distances made Einstein deeply uncomfortable because it seemed to violate this fundamental principle. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a famous paper challenging quantum mechanics. They argued that if quantum theory allows instantaneous correlations between distant particles, then it must be incomplete. There must be something missing, some hidden variables tucked behind the scenes that determine outcomes in advance. In their view, particles carry hidden information from the moment they're created, and measurements simply reveal that pre-existing information. Entanglement would then be like the classical glove example. The correlations exist because properties were determined from the beginning, not because measurement affects distant particles. But decades later, in the 1960s, physicist John Stuart Bell devised a way to test this. He derived mathematical inequalities, now known as Bell inequalities, that any theory based on local hidden variables would have to satisfy. Quantum mechanics, on the other hand, predicts that entangled particles will violate these inequalities in specific, measurable ways. So if you could do the right experiments, you could determine whether Einstein's hidden variable idea was correct, or whether quantum mechanics, with all its spooky entanglement, was giving the right answer. Starting in the 1970s and continuing through subsequent decades, physicists performed increasingly sophisticated versions of these tests. Alain Aspect in France conducted landmark experiments in the 80s. Anton Zeilinger and others pushed the boundaries further, closing various loopholes and refining the measurements. Every single time, the results supported quantum mechanics. Entanglement is real. The correlations between entangled particles cannot be explained by local hidden variables. The particles truly do exhibit coordinated behavior that defies classical locality. In 2022, Aspect, Zeilinger, and John Clauser were awarded the Nobel Prize in Physics for their groundbreaking work proving that quantum entanglement is a genuine feature of nature, not a mathematical artifact or measurement error. Their experiments demonstrated beyond reasonable doubt that the universe really does allow these strange instantaneous correlations between distant particles. It's important to clarify what entanglement doesn't allow. You cannot use entanglement to send messages faster than light, which would break causality and create all sorts of paradoxes. While entangled particles react instantly to each other's measurements, the outcomes are fundamentally random. You can't control what result you'll get when you measure your particle. You can't encode information in it. When you measure your entangled photon and it comes up vertically polarized, you know the distant photon will be horizontally polarized, but you couldn't force your photon to be vertical. The measurement result is random from your perspective. Since neither party can control their measurement outcomes, neither can send a signal to the other. The instant connection is real, but it's utterly useless for communication. It's like two people on opposite sides of the galaxy flipping coins. Each flip is random, but somehow mysteriously, whenever one person gets heads, the other always gets tails. They're perfectly correlated, but neither can send messages because they can't control what their coin shows. What's truly remarkable about entanglement is that the connection doesn't weaken with distance. You could separate two entangled particles by the width of a room, a continent, or a light year, and the entanglement would remain intact. There's no known. Experiments have successfully entangled particles over hundreds of kilometers using satellites in space, and the quantum correlations persist exactly as predicted. But what is entanglement fundamentally? Is it a kind of invisible thread connecting particles, a shared identity smeared across space, some subtle form of information distributed between quantum systems? The truth is, we're not entirely sure. Different interpretations of quantum mechanics offer different perspectives. Some view entanglement as reflecting correlations in our information about the system, not something physical in the particles themselves. Others see it as evidence of a deep, non-local fabric to reality, where separation in space doesn't mean what we think it means. There's even speculation that entanglement isn't just a quirky quantum trick, but a fundamental feature of space-time itself. Some cutting-edge theoretical work suggests that space-time, the very geometry of the universe, might emerge from networks of quantum entanglement. If that's true, entanglement wouldn't happen in space. It would be what creates space. That's a bold and speculative idea still under investigation, but it hints at just how central entanglement might be to the structure of reality. And entanglement has practical applications beyond testing fundamental physics. It's the foundation of quantum teleportation, which, despite the name, isn't about beaming physical objects, Star Trek style, but about transferring quantum states from one location to another using entanglement and classical communication. It enables quantum key distribution for secure communication, where any attempt to eavesdrop disrupts the entangled states and reveals the intrusion. In quantum computing, entanglement allows for complex operations involving many qubits that can't be reduced to simple independent processes. It's part of what gives quantum computers their unique computational power. Entanglement reminds us that the universe is deeply interconnected at the quantum level. It's not simply a collection of independent objects bouncing around in empty space. There are subtle links, invisible correlations, ways in which distant parts of the cosmos remain tied together even when separated by vast gulfs. Separateness, at least at the quantum scale, can be an illusion. The universe is more like a web than a collection of isolated pieces. Einstein may have been uncomfortable with spooky action at a distance, but even he couldn't deny the mathematical elegance and experimental success of quantum mechanics within its domain. And while we still don't have a complete, unified theory that merges quantum mechanics with general relativity, both frameworks remain astonishingly successful in their respective realms. Entanglement is now an established fact of nature, proven by countless experiments and harnessed in emerging technologies. So even though we don't see entanglement in everyday life, even though you don't wake up entangled with your neighbor or find your coffee mysteriously correlated with someone else's tea on the other side of the world, at the tiniest levels, this silent partnership between particles hums away everywhere, all the time. And maybe that's the most astonishing part, that even in a universe of vast distances and lonely spaces, there are still echoes of togetherness, instant, invisible, utterly real, woven into the very foundation of how reality works. Schrödinger's equation, the quantum heartbeat. If there's one piece of mathematics that whispers through the entire edifice of quantum mechanics like a secret spell, it's Schrödinger's equation. Now, Don't worry, this isn't going to turn into a math lecture. Nobody's getting out of bed to solve differential equations in the middle of the night. But this particular equation deserves attention because it's not just a string of symbols scribbled on a blackboard. It's the quiet heartbeat of the quantum world, the mathematical expression that governs how quantum systems evolve and change over time. Back in the 1920s, physicists were wrestling with how to describe particles that didn't behave like particles at all. Electrons showed wave-like patterns, photons acted probabilistically, and the old Newtonian laws of motion, which worked beautifully for planets and cannonballs, completely failed when applied to atoms. The quantum world needed a new language, a new framework, and that's what Erwin Schrödinger provided in 1926 when he formulated his famous equation. Schrödinger's equation describes not just where particles are or how they move, but how their wave functions evolve over time. Remember, the wave function is a mathematical object, often denoted by the Greek letter psi, that encodes everything quantum mechanics can tell us about a system. It describes probabilities, possible locations, possible momenta, all the potential outcomes for measurements. The wave function is like a probabilistic cloud, and Schrödinger's equation tells us how that cloud changes and ripples as time passes. Let's step away from the symbols and focus on what this really means. The wave function doesn't give us hard answers about where a particle is. It gives us likelihoods, probabilities. If you picture a particle as a tiny dot moving through space in a definite path, classical physics draws a neat arrow showing exactly where it is and where it's going. Schrödinger's quantum world doesn't do that. Instead, it gives us a hazy, shimmering cloud that says the particle might be here with some probability, or there with another probability, or maybe over in that direction with yet another probability. The particle isn't precisely located until you measure it. Schrödinger's equation lets us evolve this cloud through time. It shows how the probabilities shift and flow as the system develops. When a particle moves, or rather when the wave function describing the particle evolves, Schrödinger's equation tracks how the probabilities change. It's a deterministic equation governing a probabilistic object, which is an interesting twist. The evolution of the wave function is smooth, continuous, and perfectly predictable using the equation. But when you actually measure the particle, when you look to see where it is, the wave function collapses. The cloud suddenly condenses into a single definite outcome. That collapse is abrupt and random within the bounds of the probabilities given by the wave function. This wave-based view of reality is profoundly different from the mechanical, clockwork picture of the universe that dominated before quantum mechanics. Instead of particles tracing predictable paths like planets orbiting the sun, we now see swirling fields of probability. Clouds of potential outcomes that only crystallize into definite realities when measurements force them to choose. Let's bring this down to something more visual. Imagine you're blindfolded and standing in a dark room. Somewhere in that room, there's a cat. You can't hear it or see it, but you can toss little balls around and listen for when they hit something. Over time, you start building a mental picture of where the cat might be. Some regions have higher probability because that's where the balls seem to land more often. Other regions have lower probability. That mental map you're building is a bit like the wave function. It's not a picture of reality as it definitely is, but as it might be, weighted by likelihood. Now imagine you could write an equation that tells you how that map changes over time. Maybe the cat likes to move toward corners or prefers sitting near warm spots. The equation would guide your expectations about where the cat is likely to be next. That's analogous to what Schrödinger's equation does for quantum particles. It doesn't tell you exactly where the particle is, but it tells you how the probability cloud evolves. The actual equation itself is elegant and compact. It's a linear differential equation, which means it respects certain symmetries and mathematical properties that make the physics work out beautifully. It conserves energy and probability. It allows quantum states to superpose, meaning if two states are solutions, their combination is also a solution. And importantly, it accurately predicts an enormous range of phenomena, from the structure of atoms to the behavior of molecules, from semiconductor physics to the workings of lasers. One of Schrödinger's equation's greatest triumphs was explaining the structure of the hydrogen atom, the simplest atom in the universe with just one proton and one electron. Before quantum mechanics, nobody could fully explain why electrons around a nucleus seem to settle into specific stable orbits instead of spiraling inward or wandering off. Classical electromagnetism predicted that an accelerating charge, which an orbiting electron certainly is, should radiate energy and spiral into the nucleus. Atoms should be unstable, but obviously, atoms are stable. We exist after all. Schrödinger's equation revealed the solution. Electrons don't whiz around the nucleus like miniature planets orbiting a sun. Instead, they form standing wave patterns, stable configurations of the wave function around the nucleus. These are the famous atomic orbitals you might have seen illustrated in textbooks. Soft, cloud-like shapes representing regions where the electron is likely to be found. These aren't fuzzy trajectories, they're probability distributions. The electron isn't moving around in a defined orbit. It exists as a wave spread across space, and the square of the wave function's amplitude at any point gives the probability of finding the electron there if you measure it. These orbitals exist in specific energy levels, quantized states with discrete energies. Electrons can't have just any energy. They can only occupy these particular levels. When an electron jumps from one level to another, it absorbs or emits a photon with energy equal to the difference between levels. This explains atomic spectra, the specific colors of light that atoms emit or absorb, and it does so with stunning accuracy. Schrödinger's equation doesn't just hand-wave an explanation. It predicts the exact wavelengths, the exact energies, matching experimental observations to many decimal places. It's remarkable how well this equation has aged. Unlike many theories that need patches or caveats as new data comes in, Schrödinger's equation has stood the test of time with minimal modification. It works. It predicts. It's been used to design technologies from transistors to MRI machines, from understanding chemical bonds to exploring the properties of superconductors. You can't hold a wave function or see it directly, but it's there, quietly describing the ghostly potential of everything from an atom in your tea to the electronics enabling you to watch this video. And then there's the philosophical side, which Schrödinger himself found troubling. What is a wave function really? Is it a description of our knowledge, our ignorance about the system's true state, or is it an actual part of physical reality? Something that truly exists until it collapses. Different interpretations of quantum mechanics argue fiercely about this. Schrödinger gave us the mathematics, but the meaning remains debated. Interestingly, even Schrödinger wasn't entirely comfortable with the implications of his own work. He famously proposed the thought experiment of the cat in the box to critique the idea that quantum superpositions could apply to macroscopic objects. He gave us the equation, then questioned what it really meant about the nature of reality. But whatever its ultimate philosophical interpretation, Schrödinger's equation is undeniably beautiful and powerful. In a world that demands yes or no, here or there, Schrödinger offered something gentler, a shimmer of maybe, a softly pulsing guide to what could be. His equation doesn't shout or command. It suggests, it flows, and in doing so, it reveals a version of the universe that's quieter, subtler, and far more mysterious than anyone could have imagined before quantum mechanics arrived. At the tiniest scales, motion isn't always simple movement. Position isn't always a definite location. Certainty is a luxury, not a given. But thanks to one elegant equation, we can still navigate through the haze gently and mathematically, finding our way in a reality that's fundamentally probabilistic. Quantum tunneling, passing through walls. In the everyday world, walls are pretty straightforward. If you throw a tennis ball at a brick wall and the ball doesn't have enough energy to break through or go over, it bounces back. Simple, predictable. The universe says, "Nice try," and your ball obeys the laws of classical physics like a well-behaved object. Barriers are barriers. If you don't have the energy to overcome them, you don't get through. End of story. But in the quantum world, where predictability takes a permanent vacation, particles can do something that seems utterly impossible by classical standards. A quantum particle can approach a barrier, not have enough energy to overcome it, and yet still show up on the other side. No smashing through, no climbing over, no squeezing through cracks. The particle simply appears on the far side of the barrier as if the obstacle wasn't quite as solid as we thought. This phenomenon is called quantum tunneling, and it's one of those quantum effects that makes you blink, rub your eyes, and wonder if reality is having a laugh at our expense. But tunneling is very real, measurable, and fundamental to how the universe works, and surprisingly, it all comes down to probability and the wave nature of particles. To understand tunneling, we need to revisit wave functions. In quantum mechanics, particles aren't just tiny dots zipping around. They're described by wave functions that represent spreads of probability across space. These waves can extend over regions, fading gradually instead of stopping abruptly at sharp boundaries. Now imagine a particle approaching a barrier, a region of space where the potential energy is higher than the particle's kinetic energy. Classically, this would be a hard stop. The particle doesn't have enough energy to climb the potential hill, so it gets reflected back. Game over. But quantum mechanically, the wave function describing the particle doesn't vanish abruptly at the barrier. It tapers off, decaying exponentially inside the forbidden region, but never quite going to zero immediately. If the barrier isn't too wide or too tall, that decaying wave function can make it to the other side. And if part of the wave function exists on the far side of the barrier, there's a non-zero probability that the particle itself will be found there when measured. The particle doesn't have enough energy to go over the barrier, but its wave function can leak through. And because the wave function represents probability, there's a small but real chance the particle tunnels through and appears on the other side. It's not magic. It's just quantum mechanics, built into the mathematics of how probability waves behave. The tunneling probability depends on the barrier's height, width, and the particle's energy. Tall, wide barriers are harder to tunnel through. narrow, low barriers are easier. But there's always some chance, however tiny, as long as the wave function hasn't completely decayed to zero before reaching the far side. This might sound abstract, but quantum tunneling has very concrete, observable consequences, especially at the atomic and subatomic scales. Take radioactive decay, for instance. Some atomic nuclei are unstable and decay by ejecting particles like alpha particles, which are essentially clusters of 2 protons and 2 neutrons. These alpha particles are trapped inside the nucleus by the strong nuclear force, held in by a powerful potential barrier. Classically, they don't have enough energy to escape. They're stuck. But quantum mechanically, the alpha particles are constantly trying to tunnel through the barrier. Their wave functions extend slightly beyond the nuclear boundary, and there's always a tiny probability of tunneling out. Over time, even a small probability adds up. Eventually, an alpha particle tunnels through the barrier and escapes. That's radioactive alpha decay. Without quantum tunneling, many elements would never decay, and nuclear physics as we understand it would grind to a halt. Tunneling is what makes radioactive isotopes radioactive. Tunneling is also critical for nuclear fusion, the process that powers stars, including our Sun. In the cores of stars, hydrogen nuclei are smashed together under immense pressure and temperature, trying to fuse into helium and release energy. But there's a problem. Hydrogen nuclei are positively charged protons, and like charges, repel. The electromagnetic repulsion between protons creates a potential barrier that prevents them from getting close enough to fuse. According to classical calculations, even the extreme temperatures and pressures in stellar cores aren't quite enough to give protons the energy needed to overcome this barrier. Fusion should be much rarer than it actually is, but thanks to quantum tunneling, protons don't need to go over the barrier. They can tunnel through it. At the high temperatures in stars, protons get close enough that their wave functions overlap significantly. There's a small probability that they'll tunnel through the electromagnetic barrier and get close enough for the strong nuclear force to take over and fuse them together. That small probability, multiplied by the unimaginable number of protons colliding in the Sun every second, results in a steady, sustained fusion reaction. The Sun shines because of quantum tunneling. Without it, stars might never ignite, and the universe would be a much darker, colder place. Here on Earth, we've harnessed tunneling for practical applications. One elegant example is the Scanning Tunneling Microscope, or STM. This device allows scientists to visualize surfaces at the atomic level, literally imaging individual atoms. It works by bringing an ultra-sharp metallic tip extremely close to a surface, just a few nanometers away, close enough that the gap between tip and surface is comparable to atomic distances. At that tiny separation, electrons can tunnel between the tip and the surface. When you apply a voltage, electrons tunnel across the gap, creating a measurable current. The size of that tunneling current depends sensitively on the distance. Move the tip closer, the current increases. Move it farther, the current decreases. By scanning the tip across the surface and measuring the tunneling current at each point, the microscope builds up an incredibly detailed map of the atomic landscape. What's remarkable is that the STM doesn't touch the surface. It's imaging purely through quantum tunneling, through the ability of electrons to slip across empty space and into the detector. This non-contact technique gives scientists a way to peer into the quantum terrain with stunning precision, revealing the positions of individual atoms and even manipulating them. It's a beautiful demonstration of quantum mechanics, not as an abstract theory, but as a practical tool for exploring the nanoscale world. Tunneling also plays a role in electronic components like tunnel diodes and flash memory. In modern electronics, as transistors shrink to nanometer scales, we're reaching quantum limits where electrons can tunnel through barriers that classical physics would consider solid insulators. This creates challenges as unwanted tunneling causes leakage currents and noise, but it also opens opportunities for devices that deliberately exploit tunneling for specialized functions. Quantum dots, resonant tunneling diodes, and other nanoelectronic devices rely on carefully controlled tunneling to achieve properties impossible with classical components. At its core, quantum tunneling teaches us something profound about the nature of barriers and boundaries. We often think of the world as made of hard edges. You can go here but not there. You have enough energy or you don't. But the quantum world is more nuanced. Barriers aren't impenetrable walls. They're probabilistic, suggestions rather than absolutes. Particles don't follow strict either-or rules. They exist in a realm of maybe, where forbidden regions are merely very unlikely rather than strictly impossible. And while this might feel unsettling, it's also strangely elegant. Because of tunneling, particles aren't confined rigidly to the paths we imagine. They can cheat, slip through, blur the lines between possible and impossible. They remind us that the universe isn't a machine made of perfect gears turning in predetermined ways, but rather a shimmering interplay of likelihoods and possibilities. The tennis ball might bounce off the wall every single time in the macroscopic world. But the electron, the photon, the alpha particle, they glance at that same wall and sometimes decide to take the shortcut straight through. And somehow, inexplicably, nature lets them do it, governed by the strange and beautiful mathematics of quantum mechanics. The quantum vacuum. Nothing isn't empty. In everyday life, we think of nothing as, well, nothing. The absence of stuff. An empty room is empty. A blank page is blank. The space beneath your bed where socks mysteriously vanish is just empty space. And when we extend this idea to physics, we imagine the vacuum of space as a perfect void, cold, silent, and utterly devoid of anything. Zero particles, zero energy, zero activity. Just emptiness stretching infinitely in all directions. But in quantum physics, nothing is never really empty. What we call the quantum vacuum, the lowest energy state where all particles have been removed and no fields are actively doing anything, isn't a serene, motionless void. It's a restless, jittering stage where invisible activity constantly bubbles and seethes. At the smallest scales, even when there's nothing there in the classical sense, space itself is alive with quantum fluctuations. Waves rise and fall. Virtual particles flicker in and out of existence, and the vacuum hums with a low, constant energy that can't be removed. It's like the universe has a baseline level of noise, a quantum static that never quite goes silent. The reason for this perpetual activity traces back to Heisenberg's uncertainty principle. Remember, the uncertainty principle doesn't just apply to position and momentum. It also applies to energy and time. That means even in a region of space where the average energy should be zero, the energy can briefly fluctuate, spiking upward for tiny fractions of a second before returning to zero. These fluctuations give rise to virtual particles, which appear spontaneously from the vacuum, hang around for a fleeting moment allowed by the uncertainty principle, and then vanish as if they never existed. They're called virtual not because they're imaginary, but because they can't be directly observed in the usual sense. They exist only in the fleeting gaps permitted by quantum uncertainty. But their effects are very real and measurable. These quantum blips influence physical systems in subtle but detectable ways, proving that the vacuum isn't empty at all. It's teeming with transient ephemeral activity. One of the most striking examples of this is the Casimir effect, named after Dutch physicist Hendrik Casimir, who predicted it in 1948. The Casimir effect is one of those rare phenomena where the quantum vacuum does something tangible, something you can actually measure in a laboratory. Here's how it works. Imagine placing two very thin, perfectly conducting metal plates extremely close together in a vacuum, just a few nanometers apart. According to classical physics, nothing should happen. There's no matter between the plates, no forces acting on them, just empty space. The plates should sit there, inert and indifferent. But quantum mechanics says otherwise. Because the gap between the plates is so narrow, only certain wavelengths of virtual particles can exist there, specifically wavelengths that fit neatly between the boundaries. It's like only certain musical notes can resonate in a narrow pipe. Outside the plates, however, there's no such restriction. The full spectrum of virtual particle wavelengths can exist in the open space beyond. This creates an imbalance. There's slightly more pressure from virtual particles outside the plates than between them. The result is a tiny but measurable force pushing the plates together. The Casimir effect has been observed in precise laboratory experiments, and the measurements agree beautifully with quantum predictions. It's a direct demonstration that the vacuum isn't empty, even in the absence of any real particles. The quantum vacuum exerts forces, nudges matter, and leaves detectable fingerprints. It's as if empty space itself is gently squeezing the plates together, proving that nothing has structure, energy, and physical consequences. This vacuum energy isn't just limited to quirky lab experiments, it plays a role across the entire universe. In cosmology, there's the concept of vacuum energy density, the idea that even the emptiest regions of space have a baseline energy associated with quantum fluctuations. Some physicists believe this vacuum energy might be responsible for dark energy, the mysterious force driving the accelerating expansion of the universe. We don't fully understand dark energy, but the notion that quantum vacuum fluctuations contribute to it is a tantalizing possibility. There's a catch though, and it's a big one. If you try to calculate the total vacuum energy of the universe using quantum field theory and particle physics, you get a number that's absurdly, catastrophically wrong. The predicted vacuum energy is about 120 orders of magnitude larger than what we actually observe. That's not a small error. It's the worst prediction in the history of physics, a mismatch so enormous it's become known as the cosmological constant problem. Nobody knows how to reconcile the theoretical prediction with the observed value. It's one of the deepest unsolved mysteries in physics, hinting that we're missing something fundamental about how quantum mechanics and gravity fit together. But even setting aside cosmological mysteries, vacuum fluctuations play a crucial supporting role in particle physics. In quantum electrodynamics, the theory describing how light and matter interact, particles constantly exchange virtual photons. These exchanges mediate the electromagnetic force. An electron doesn't just sit there in isolation. It's surrounded by a cloud of virtual photons flickering in and out of existence. And those virtual photons influence the electron's properties. They slightly shift the electron's energy levels in atoms, an effect called the Lamb shift, which has been measured with extraordinary precision. The vacuum, with its virtual particles, actively shapes the behavior of real particles. Even the mass of particles like protons is affected by vacuum fluctuations. Inside a proton, quarks are held together by the strong nuclear force mediated by gluons. But the proton's mass doesn't come just from the quarks. Most of it comes from the energy of the gluon field and the constant interactions within. The interior of a proton is a seething soup of virtual quarks and gluons, and that quantum activity contributes to what we perceive as the proton's mass. What we think of as stable solid matter is really the result of constant quantum turmoil. The quantum vacuum also affects measurements in atomic physics. When physicists calculate the precise energy levels of electrons in hydrogen atoms, they have to account for vacuum fluctuations. Without including those corrections, the theoretical predictions wouldn't match experiments. But when you factor in the effects of virtual particles, the calculations align with observations to incredible accuracy, sometimes agreeing to 12 decimal places. The vacuum is woven into the fabric of every measurement, every interaction, every particle. In a way, the quantum vacuum is the most fundamental field of all. Every other field, electromagnetic, gravitational, nuclear, exists within it. They ripple and hum against this baseline background, like instruments playing melodies over a constant drone. Some physicists even speculate that the vacuum holds clues to deeper truths about quantum gravity, the unification of quantum mechanics and general relativity, or even the structure of space-time itself. What's humbling is realizing that even in the coldest, darkest, most isolated regions of space, where matter is scarce and starlight is a distant memory, the quantum vacuum is still there, vibrating, jittering, whispering the rules of existence to anything willing to listen. Nothing is never truly nothing. Even in apparent stillness, the universe teems with hidden activity. In the pauses between moments, in the gaps between particles, in the silence between stars, something is always happening. We live not on a quiet, passive stage, but on one that murmurs beneath our feet. And while we may not hear it with our ears or see it with our eyes, physics has found the instruments to detect and measure those murmurs. The vacuum hums, particles flicker, reality dances to a rhythm we've only just begun to understand. A rhythm that never stops, not even when everything else has fallen silent. Quantum computing, harnessing the weird. If classical computers are like carefully trained librarians, efficient and methodical, flipping through records one page at a time, then quantum computers are more like very strange poets who somehow manage to read all the books at once in overlapping whispers and still find the answer you need. It sounds like magic, and in some ways it feels like magic. But quantum computing is very real. It's built on the same bizarre principles that make up the heart of quantum mechanics: superposition, entanglement, and interference. And while it's not going to replace your laptop anytime soon, it promises to revolutionize how we solve certain types of problems. To understand what makes quantum computers different, you first need to meet the bit's weirder cousin, the qubit, short for quantum bit. In a classical computer, everything boils down to bits, binary units of information that can be either 0 or 1, like a switch that's off or on. These bits are the building blocks of everything your devices do. Every photo, every song, every video, every app is just long strings of zeros and ones processed at lightning speed. A qubit, on the other hand, doesn't just live in a state of 0 or 1. Thanks to quantum superposition, a qubit can be in a blend of both states at once. Think of a spinning coin in the air, neither heads nor tails until you catch it and force it to commit to one face. While it's spinning, it holds the potential for both outcomes. Similarly, a qubit exists in a quantum superposition of 0 and 1 simultaneously, not flipping between them but genuinely occupying both states until measured. This means a single qubit holds more information than a classical bit in a certain sense. And as you add more qubits, the power grows exponentially. 2 qubits can represent 4 possible combinations simultaneously. 3 qubits can represent 8. 20 qubits can represent over 1 million combinations. The number of states explodes at an exponential rate. With enough qubits, a quantum computer can in principle explore an astronomical number of possibilities in parallel, at least in a mathematical sense. But here's the crucial part. It's not quite as simple as getting all the answers at once. Quantum computing doesn't magically give you every solution simultaneously. Instead, it uses superposition to explore many possibilities in parallel, and then employs quantum interference to amplify the correct answers and cancel out the wrong ones. The process is subtle, relying on carefully designed quantum algorithms that guide the system, so that when you finally measure the qubits, the right answer is the most probable outcome. It's like shaping a probability landscape so the solution rises to the top. And there's another quantum trick: entanglement. When qubits become entangled, the state of one is linked to the state of another, even across separations. This creates complex correlations that classical bits simply can't replicate. Entangled qubits can work together in ways that allow quantum computers to perform operations impossible for classical machines. It's like a synchronized dance where each dancer's moves depend on what all the other dancers are doing simultaneously. For certain problems, particularly those involving optimization, simulating quantum systems, or factoring large numbers, quantum computers offer dramatic potential speedups. Algorithms like Shor's algorithm for factoring integers and Grover's algorithm for searching databases can exploit quantum superposition and entanglement to solve problems exponentially or quadratically faster than the best-known classical algorithms. This has enormous implications for cryptography, materials science, drug discovery, artificial intelligence, and many other fields. But now, let's slow down and inject a dose of realism. Quantum computers are not going to replace your laptop or smartphone for everyday tasks. They're highly specialized tools for things like browsing the web, editing documents, playing videos, streaming music. Classical computers are perfectly fine and far more practical. Quantum computers excel at specific types of problems that involve massive parallelism or simulating quantum systems. They're not general-purpose devices, at least not yet, and may never be for most common applications. Building and running quantum computers is also extraordinarily difficult. Qubits are incredibly delicate. They can be disrupted by the tiniest vibrations, fluctuations in temperature, stray electromagnetic fields, even cosmic rays passing through the lab. Maintaining a qubit's coherence, its ability to stay in superposition and entanglement, requires extreme isolation and control. Many quantum computers operate at temperatures near absolute zero, colder than the depths of space, to minimize thermal noise. Even then, Qubits can only hold their quantum states for fractions of a second before decoherence sets in and the quantum information is lost. Error correction is another huge challenge. In classical computers, if a bit flips unexpectedly, you can detect it and fix it relatively easily. In quantum systems, things are much trickier. You can't simply copy a qubit state to make backups because of the no-cloning theorem, a fundamental result in quantum mechanics that says you can't create perfect copies of unknown quantum states. Instead, physicists have developed elaborate quantum error correction schemes that use many physical qubits to protect a single logical qubit. It's like wrapping your whisper-quiet poet in layers of soundproof insulation, so external noise doesn't destroy the delicate quantum calculations. Despite these challenges, progress has been impressive. Companies like IBM, Google, and startups around the world have built quantum computers with tens to hundreds of qubits. Google made headlines in 2019 when they claimed to have achieved quantum supremacy, demonstrating a quantum computer performing a specific task that would take an impractically long time for the best classical supercomputers. Other groups are exploring different types of quantum systems: superconducting qubits, trapped ions, topological qubits, photonic qubits, each with different strengths and weaknesses. Researchers are also developing intermediate devices known as NISQ machines, which stands for Noisy Intermediate Scale Quantum. These are quantum computers that aren't yet error-corrected or large enough to run fully fault-tolerant algorithms, but they can still perform useful tasks and help scientists explore what quantum computing can achieve in practice. It's an exciting, rapidly evolving field where new results and breakthroughs appear regularly. Real-world applications are starting to emerge. Quantum chemistry is a promising area. Simulating the behavior of molecules at the quantum level is incredibly difficult for classical computers because molecules are inherently quantum systems, but quantum computers are naturally suited for this task. They can model chemical reactions, predict molecular properties, and help design new materials or drugs. This could revolutionize fields like materials science, pharmaceuticals, and battery technology. Optimization problems are another target. Many industries face challenges involving finding the best solution among countless possibilities, optimizing supply chains, scheduling flights, managing financial portfolios, routing traffic. Quantum algorithms may be able to find better solutions faster than classical methods, though practical implementations are still in early stages. Cryptography is both a promise and a threat. Shor's algorithm, once implemented on a sufficiently powerful quantum computer, could factor large numbers exponentially faster than any known classical algorithm. This would break widely used encryption methods like RSA, which rely on the difficulty of factoring for security. That's a serious concern for cybersecurity, and it's driving the development of post-quantum cryptography, new encryption schemes designed to be secure even against quantum attacks. On the flip side, quantum cryptography based on quantum key distribution offers provably secure communication, where any eavesdropping attempt disturbs the quantum states and reveals the intrusion. What's particularly delightful about quantum computing is how it takes the strangest, most counterintuitive parts of quantum mechanics and turns them into tools. Superposition, once a philosophical puzzle, becomes a resource for parallel processing. Entanglement, Einstein's spooky action at a distance, becomes a mechanism for correlation and coordination. Even measurement, the act of collapsing possibilities into a single reality, becomes a crucial step in extracting results from calculations. The very weirdness that made quantum theory so hard to accept is now being harnessed to solve problems thought to be intractable. Quantum computers invite us to rethink what computation even means. They challenge the boundary between certainty and probability, between classical logic and quantum interference. They remind us that beneath the surface of everyday computing lies a much stranger landscape, one where information is soft, entangled, probabilistic. And while we don't yet know exactly where quantum computing will lead, where it will succeed, or what limits it will face, the journey itself is already reshaping our understanding of what machines can do and what the quantum world can teach us about possibility. Philosophical implications and closing. As we drift gently toward the end of this exploration, it's worth pausing to reflect on what quantum physics means beyond the equations, beyond the experiments, beyond the technologies. Because quantum mechanics isn't just a set of tools for calculating probabilities or designing gadgets. It invites us, perhaps even forces us, to think differently about the nature of reality itself, about what it means to know something, and about our place as observers in a universe that behaves so strangely when we look closely. We tend to think of reality as something solid, fixed, existing independently out there, whether we're looking at it or not. A tree falls in a forest, and we assume it makes a sound regardless of whether anyone hears it. The moon doesn't vanish just because we close our eyes. Classical physics supported this intuition beautifully. Objects have definite properties. Causes lead to effects. The universe unfolds along predictable paths governed by immutable laws. But quantum mechanics gently suggests that at the smallest scales, reality isn't fixed at all. It's a set of possibilities, a collection of potential outcomes shimmering in superposition until observation nudges them into definite form. Before measurement, a particle isn't secretly in one place with us, just not knowing where. It genuinely doesn't have a definite location. It exists as a spread of probabilities, a cloud of maybe, until we interact with it and force it to choose. This raises a quiet, unsettling thought. If observation plays such a crucial role in shaping outcomes, are we observers truly separate from the universe we're studying? Or are we participants, entangled in the grand quantum dance? Quantum mechanics doesn't necessarily require conscious observers to collapse wave functions. Measurement can be any interaction that extracts information, any event that couples a quantum system to the environment. But the fact remains that observation matters, that the act of looking or measuring or interacting changes things in ways that have no classical analog. For physicists, these are technical questions with implications for how we interpret mathematics. For the rest of us, they feel almost spiritual. They remind us that our everyday intuitions about space, time, matter, causation are just approximations, useful guides for navigating the macroscopic world, but not the final word on how things actually work at the deepest levels. Quantum mechanics also invites humility. It reminds us that the familiar world we experience, the one of solid objects and predictable trajectories, is just one version of reality, filtered through evolution and shaped by our senses. Our brains evolved to hunt, gather, avoid predators, and build shelters. They did not evolve to intuitively understand wave functions or quantum entanglement. The quantum world isn't obligated to make sense to creatures operating at human scales. And yet, through mathematics, through careful experimentation, through centuries of collective intellectual effort, we've managed to peek behind the curtain and glimpse a reality far stranger than our ancestors could have imagined. Think of Schrödinger's cat again, not as a literal feline trapped in paradox, but as a metaphor for how we live with uncertainty every day, waiting for medical test results, applying for a job, wondering if it will rain tomorrow. We exist in states of not quite knowing, juggling conflicting possibilities, hope and fear coexisting until time or circumstance collapses the wave, and we discover which reality we're in. Quantum mechanics formalizes this experience at the smallest scales, showing that uncertainty isn't just a limitation of knowledge, but a fundamental feature of how the universe operates. And maybe there's a quiet freedom in that realization. If certainty isn't guaranteed, then neither is limitation. If the world isn't pinned down until it's observed, then possibility is always alive, flickering just beyond our immediate perception. The universe isn't a rigid machine grinding through predetermined outcomes. It's more like a field of potential, open, responsive, full of paths not yet taken. Even the word quantum has a kind of poetry to it. It comes from Latin meaning how much, a question about quantity and measurement. But at its heart, quantum mechanics asks deeper questions. How much can we know? How much does reality commit to before we look? How much of what we see is shaped by our interaction with it? These aren't just scientific questions. They're existential ones, probing the boundaries between knowledge and mystery, between what is and what might be. Throughout this video, we've wandered through some of the most beautiful and bizarre ideas in physics. We've seen energy come in discrete packets, light behave as both wave and particle, particles tunnel through barriers, pairs of distant particles remain mysteriously connected. We've explored equations that govern probabilities, principles that set limits on knowledge, and technologies that harness quantum strangeness to compute, communicate, and measure in ways classical physics never imagined. But beyond all the details, all the experiments and mathematics, quantum physics leaves us with a sense of wonder. It shows us that the universe is weirder, more open, more surprising than we ever thought. Reality at its core is not a collection of solid, separate things bumping into each other along predetermined paths. It's a shimmering interplay of possibilities, fields of probability woven together by mathematics so elegant it almost feels like poetry. And we are part of that reality, not just observers standing outside looking in, but participants embedded in the quantum world, made of the same fields and particles, governed by the same strange rules. The atoms in your body, the light reaching your eyes, the electrons powering the device you're using right now, all of them dance to the quantum rhythm. All of them partake in the grand, mysterious, probabilistic unfolding of existence. So as we close, I want to leave you with this. The next time you look at the night sky, or hold a warm cup in your hands, or watch sunlight streaming through a window, remember that beneath the surface of the familiar lies something far stranger and more wonderful. The universe is not obligated to be simple or intuitive. It's under no requirement to make sense in ways our brains find comfortable, but through curiosity, through careful observation, through the collective effort of countless scientists asking questions and testing ideas, we've learned to see beyond appearances. Quantum mechanics doesn't give us all the answers. It gives us better questions. It teaches us to accept uncertainty, to embrace probability, to marvel at the fact that reality itself has texture and depth and mystery at every scale. And perhaps most importantly, it reminds us that knowledge is a journey, not a destination, and that even after a century of quantum theory, We're still only beginning to understand the profound strangeness of the heart of everything. If you've enjoyed this slow drift through the quantum world, if these ideas have sparked your curiosity or given you something interesting to think about, I'd really appreciate it if you'd hit that like button and subscribe to Behind the Sleep. Your support helps this channel keep exploring the mysteries of the universe, one topic at a time, in that relaxed, thoughtful way we all need sometimes. And wherever you are right now, whether you're drifting off to sleep or wide awake with thoughts spinning, I hope you found something here that resonated, something that made the universe feel a little bigger, a little stranger, and a lot more interesting than it seemed before. Thank you for spending this time with me. Thank you for your curiosity. And remember, in a quantum universe, possibility never quite disappears. It just waits, shimmering quietly, for the right moment to become real.